Hello everyone, this is Professor Roman. Welcome to the 9th video in my video lecture series and Introduction to Discrete Mathematics. Now that we know how to translate compound statements into symbolic form, we can consider the problem of finding the truth tables of statements that are in symbolic form. These truth tables will give us the truth value of a compound statement based on the truth values of the simple statements that make it up. The place to start is with the truth tables for the 5 basic connectives, because those truth tables actually define the logical meaning of each of the connectives. And again, I have to say it, those tables should be memorized. You shouldn't have any trouble with 4 of the tables because they're quite obvious. One of them has a little subtlety to it, which we'll talk about when we get to it. The truth table that describes the logical meaning of negation, the connective not, is shown here. When P is true, not P should be false. When P is false, not P should be true. Conjunction is not much more difficult than that. The logical meaning of the connective and is that in order for P and Q to be true, both P, and Q have to be true. So the first row of the table is true. P and Q are both true. P and Q is true. All the other rows are false. Disjunction, the connective or, P or Q will be true when at least one of P or Q is true. So we have 3 trues and a false. Now, there are 2 common meanings associated with the word or in the English language. Ordinary usage says that the phrase P or Q can mean either P or Q or both. Or it can mean P or Q, but not both. So there is some potential ambiguity in English. The first meaning, P or Q or both, is called the inclusive or, and the second, P or Q but not both, is called the exclusive or. I don't want to pontificate on common usage in English, but I think that or, even in English, generally refers to the inclusive or, but you may have to clarify that when you're talking to somebody, because they may interpret it as the exclusive or. In mathematics, however, or and the symbol we use for it always refers to inclusive or. Okay. Now we come to the conditional, which is the one I mentioned earlier that's a little bit subtle in spots. There's some important terminology that goes with the conditional statement, so let me clarify that first. In the statement A implies B, A itself could be a compound statement, so it could be, it doesn't matter. A, the part that comes before the arrow, is called the hypothesis or the antecedent. I will tend to use the word antecedent. B is referred to as the conclusion or the consequent. Okay, now when defining the truth table for the conditional, I think the first 2 rows seem fairly obvious. If both the antecedent and the consequent are true, then P implies Q is true. if the antecedent or hypothesis is true, but the conclusion is false, something went wrong in the reasoning. P implies Q should be false. Now we come to the last two rows. And if you search the internet, look in other books, you will find a variety of explanations for what should be here in place of these question marks. The answer is they should both be true. And oftentimes students are a bit confused by that. Well, as I say, there are a lot of different ways to look at it, but here is one way. Consider this statement. P implies P or Q. Okay. Now, if you think about this, I think you should see that this statement should always be true. P implies P or Q. In a way, the Q is kind of irrelevant. P implies P certainly should be true, and therefore so should P implies P or Q. P implies P and Q would not be true, but P implies P or Q should be. Well, here is a table I constructed. The first two rows are the same as they are here, true and false. So in each case there are four possibilities. We always have true, false, true, false, true, false for the first two rows. Here are all the possible combinations for the second two rows. Both true, true, false, false, true, and false, false. Now we fill in the rest of this table with using the various possibilities for the last two rows of this table. Okay? Both true, true, false, false, true, false, false. If you try them all, you will discover that only one possibility makes P, where'd it go? Makes P implies P or Q true. Always true. Okay. This is true only under choice 1. So as a good exercise, I'll let you fill in the tables if you want. You're going to have to create 4 truth tables, one for each of these 4 possibilities for P implies Q. Okay. So if we want this to always be true, we have no choice but to put trues in both these last 2 spots. And this is then the truth table for the conditional. It may seem weird, false, if the point here is that if the hypothesis is false, if the antecedent is false, it doesn't make any difference what the consequent is, true or false. The whole conditional is true. And that sounds a little weird at first, but it's the only thing that makes, the only possibility that makes P implies P or Q a true statement. At least we have one benefit. It's relatively easy to remember this truth table. The only time a conditional is false is when it is pretty much obviously false. The hypothesis is true, but somehow that leads you to a false conclusion. That should be false. Otherwise, the conditional is true. We won't have any real issues with the biconditional if and only if. P if and only if Q is true precisely when both P and Q are true, or P and Q are false. In other words, when they have the same truth value, P and Q. So there's a true here and a true here, and the middle ones are false. Again, I will say, you probably should not continue until you have these 5 truth tables firmly fixed in your head. We can now construct, for example, a truth table for this compound statement. And the way it is done in general is to use intermediate columns. So we have our column for P and for Q, and by the way, I am always listing them two trues, true, false, false, true, false, false. Technically, you can put these in any order you want, and some books actually reverse this. The first 2 will be false, the last 2 will be true. I'm not sure about them. I guess this would be false, true, and true, false. I find that very annoying because I'm so used to this. But the point is, you need to look at the whole table to see how the author is arranging the rows. Anyway, the next step after you've done the first 2 columns is to do a column for not Q, because that appears in the compound statement. And so you just reverse the values for Q. Now you can take the conjunction and of the first and third columns, and it might help you for a while you're practicing this to cut a strip of paper and lay it on top of the column that you don't need anymore, so it won't distract your eye, because it would be very easy to take the conjunction here of these 2 instead of the first and third, the second and third, and end up with a false here. So you need to be careful. The intermediate columns are important, especially as the compound statements get more complicated, but the downside is you'll have a bunch of columns you have to ignore at some point. So we take the conjunction of the first and third column, and this is what we get. Now, if you want to be neat and clean and present a truth table for this compound statement, you would rewrite it without the intermediate columns. That's up to you. Here's another example, very similar to the previous one, but here we have a disjunction, P or Q, so our intermediate column is going to be that disjunction. Here is one that is significantly more complicated, and here's one that's even worse, and I will let you study these. Here's one with 3 statement variables, and so we need 8 rows to cover all the possibilities, the first 3 columns, all trues all the way down to all falses. And we need 2 intermediate columns here to deal with this one and this one, and then we take the conditional for those 2 columns. In general, a truth table with n variables will require 2 to the n rows. Here we had 3 variables, 2 cubed is 8. Okay. So these can get rather large rather quickly, but computers should have no problem creating these tables should that be necessary. The compound statements in this example here and in this one here, oops, is that the one I want? they're kind of special if you look at these tables. In the first case, this compound statement is always true. In this case, the compound statement is always false. It's not at all obvious just by staring at this compound statement that it's always false. How about this one? P implies P and Q. P or Q. We already talked about that. It's always true. And that makes sense. This one's harder to unscramble, but you could. P and not P. That is false, regardless of what P is. And a conditional that has a false antecedent is always true, so when we negate it, it should always be false. There is some terminology associated with these examples. A compound statement that is always true, regardless of the truth values of the simple statements that make it up, is called a tautology. Or another term for it is logically true. Okay, logically true. It's true because of its logical construction, its syntax. And a compound statement that's always false is called a contradiction or is said to be logically false. Now, you should keep in mind, of course, that not all compound statements are either tautologies or contradictions. Most of them fall in between. For some truth values of the simple statements that make it up, the compound statement will be true, and for some it will be false. That's typical. There are times when a compound statement can be shown to be a tautology without actually having to construct its truth table. To make this idea precise, first of all, if A and B are compound statements, then we can build additional compound statements using those compound statements A and B and connectives, not A and B, A or B, A implies B, A if and only if B. Okay? So for instance, if A was this compound statement, and B was this one, then not A looks like this, A or B, disjunction, implication. Okay. This is just substitution. You replace capital A by a compound statement, you replace capital B by a compound statement. Now, theorem, if A and B are compound statements, and if A itself is a tautology, it's always true, and if A implies B is a tautology, always true, then B is a tautology, always true. And to prove this, we have to show that any assignment of truth values to the statement variables within B must result in a true statement. B is true regardless of the truth values of its component simple statements. So suppose we do make an arbitrary assignment of truth values to the variables in B. Now there may be some variables in A that are not in B, and we can do whatever we want with those. Let's say set them all to be true, okay, or set them all to be false. It doesn't matter, it's arbitrary. Okay. Well, we know that this assignment makes A true because A is a tautology. That's why it didn't matter how we assign the variables in A that are not present in B. And A implies B is true because that's a tautology. Now the definition of the conditional says that if A is true, the only way A implies B can be true is if B is true. If B is false, you have a true implies false, and that's not true. Okay. So if you're a little vague on this, it's fine. You should read it over a few times. Basically, it's much ado about almost nothing. All that matters is that when you look at the truth table for the implication for conditional, and you look in the rows that have a true antecedent, the only row that has a true conditional is the row that has a true consequent, because true implies false is not true. Okay, now we have another theorem coming up, but first let's take a simple example to illustrate. Consider this statement: P implies, and then Q implies P. If you check this with the truth table, you will see it's a tautology. Now, suppose that A and B are any compound statements. Then we can replace P by A and Q by B, and it looks like this. That's also a tautology. No matter how you assign truth values to the components of A and B, you're going to end up with something that is what the truth value here, is the same as the truth value here, because they're both A's. And similarly, the truth value here is the truth value of B. So you have this same logical structure. So if this is a tautology, so is this. Well, there's nothing special about this example. So here is a theorem that is known as the substitution theorem for tautologies. Let A be a tautology, and suppose that A contains these distinct statement variables, P1 through Pn, and maybe others, but we're just concentrating on this choice. And suppose that B1 through Bn are compound statements. Then if we replace the statement variables P1 through Pn in A by B1 through Bn, and we have to do it consistently, every instance of P1 has to be replaced by B1, every instance of P2 by B2, and so on. The result is also a tautology. I didn't give the proof for this. The argument's very similar to the example I did earlier, and it would be very helpful for you to give this some thought, maybe write your own proof. Example: P or not P is a tautology. We can replace P by anything we want. I just use this, and so this is a tautology. P implies Q is a tautology. If we replace P by this rather long expression and Q by this one, again, I just picked these arbitrarily. We'll get something that looks pretty formidable. A lot of parentheses, hard to read. No question, hard to read. But we don't need to construct its truth table. It is a tautology because this is a tautology. And this is a substitution instance of this one that I've highlighted. Okay. One final thought. If S is a compound statement, we can define a function, f sub s, called a truth function or sometimes a Boolean function, in the following way. If S contains the n distinct statement variables P1 through Pn, and no others, just that's a complete list, then the truth function f sub s is a function of n variables, x1 through xn, each of which can take on the values t or f. So these are not real valued variables. They're variables whose values are either t or f. And the value of this expression is defined to be the truth value of the statement S when the variables, I got this backwards. No, that's right. When the variables P1 through Pn in S are given these truth values. Remember, the x's are either t or f. So you take these trues or falses, you stick them in for the p's in S, and that will give you a truth value. That's the value of the function. So here's a simple example. Example 92, I have to go back. I should have recopied it, my fault. Let's see, where is it? Here's the statement. Let's come down here. Here we go. So this is a function of two variables because we have two statement variables, P and Q. F sub s of true, true, you just put in the values true for both P and Q, and apparently that's false. If you said P equals true, Q equals false, compute this truth value, it's true, so the value of the function is true. I would hope you get the idea here. This is a more complicated one, but the principle is exactly the same. There's very little difference between a truth table and a truth function. The truth table is basically a table of all the function values for the truth function. Okay. But sometimes one notation is more convenient than the other, and we will in fact have use for both of them. Okay, well, I think that's enough for this video. It's a bit short, but that's okay. And in the next video, we will discuss logical equivalence, a very important concept. So thank you for watching, and I hope to see you in the next video.